I laugh with you.
Okay.
That's a big difference.
That's true. That's true. I'm going to start telling myself when people laugh around me that it's with me and not at me.
Remember, we're just a team, right?
That's right. That's right. And the team that laughs together succeeds together, right?
I agree. And I think our dean is agreeing with us. That's good.
Yes, with us, not at us.
Well said. Well said. Hello, Hamde. Alisha Tori.
How are you? I'm good.
Good. I bet Ali didn't know that I could speak some Farsi.
Farsi.
Well, I mean, it's...
And you have a good accent.
Thank you. Thank you. Well, good luck with the presentation. I'm sure it'll be great.
Thank you.
I think we have 16 so far. So I guess we can wait one more minute and we'll start. It's 11, but we'll give 1 minute bonus.
Dr. Faris, do you believe only in odd numbers?
Hey, Krish, how are you doing? No, all numbers are great, especially if there is a dollar sign in front of them.
It's also a prime number.
It's so great to have Dr. Krish in attendance, VIP. So appreciate it, Krish.
Oh, thank you. It sounds like an interesting seminar. So
thank you.
All our seminars are interesting. I learn something new from everyone.
The problem is whether I can follow. So that is always the determining factor.
By the way, you had a good show yesterday too with the what do you call it? The Zoom, the mini
Data Blitz.
Data Blitz, yeah.
Yes.
And Dr. Veera Surya took part. Very interesting.
Oh, thank you. Thank you for attending.
Thanks for organizing.
Sure, no problem.
What's up? What happened?
Okay, I think we can start. Good morning, everyone, and welcome to the Research Seminar Series. We would like to, first of all, give you a quick update. I'm sharing with you my screen, and I hope you see it. You've seen it, right?
Yes.
Yes.
So, as you have seen last week, we started a mini series within the series. It's on precision agriculture. We will have additional speakers this coming week. And after that, also on the, I think, on the 22nd too. So the 15th, we won't be able to have a seminar presentation because we have the LDE. So, and most of us will be busy participating and welcoming our students and on the competitions, etc. So I think with that, we won't have seminars, but you can see that we will be having Dr. Nachodhuri on the 8th from the Department of Engineering and University of Maryland East Shore. And after that, on the 22nd of October, we will have Dr. Zhang and Dr. Green from USDA ARS Fort Collins.
Since it is a different account.
So they will be talking to us about their research in
to,
precision agriculture.
So did you log into your HD account?
HD account also on the 29th of October, we have another two presenters.
Okay. So you have HD account also,
Dr.
right?
Dooley and Dr. Redwine from TAMU. They will, especially from the Department of Agriculture Leadership, Education, Communication, they will be talking to us about the use of technology to improve teaching and learning, and also international agriculture communication and development. So these are great
my Zoom account.
Topics
then I'll be disconnected there. That's why I told you not to.
Please encourage our students.
That's why I was telling you not to disturb me.
Seminars. I found it very, very helpful to our students. I usually give them bonus if you attend the seminar and you do something quick. I give you a couple of points in an exam or a test. So I think it's very helpful, and they really respond positively. So please encourage our students. For this week's presentation, I'm pleased to introduce to you Dr. Hamida Habibi. So Dr. Habibi, she's working with us as postdoctoral research fellow. She's mentored by our colleague, Professor Rupendra Awal. She received her PhD from the University of Texas at Arlington in civil engineering with specialization in water resources in 2017. And in 2018, she joined our group here in CARP. Since then, she has been with us. Her MS and BS degree were in civil and agriculture engineering in Iran. So she has Aggie background, so she's not foreigner to agriculture. So she's back to her, I think, original home degree. So she has over 7 years of research experience in water resources planning and management, specifically on flash flood forecasting, integrated modeling, crowdsourcing. This is not for funding. This is for flood prediction and etc. So she also has modeling experience in 1D and 2D modeling, remote sensing, and statistical analysis. In her doctoral degree program, she developed a real-time high-resolution flash flood forecasting system for Dallas-Fort Worth area, and also a storm drain module that can be coupled with any gridded distributed hydrological model for real-time flash forecasting of large area. And she worked on using RDHM, which is a model that National Weather Service uses until recently for flood forecasting across the United States. Also, similar work Dr. Awal conducted on Hawaii, performing basically testing the performance of the same model in Hawaii. Right now, National Weather Service is switching from RDHM to Wharf Hydro. And Dr. Habibi and Dr. Awal and our group are following that pattern because that's where the national interest is and that's what we are moving towards. So if the end of the presentation, Dr. Habibi will share with us a couple of slides of what we have been doing in this area to be up to date in research about flooding. These are some of the publications that Dr. Habibi published or was part of it since she joined us here in the group. There are at least 3 additional publications that are either in the pipeline or submitted, so that are not represented in this slide. So as you can see, she has been productive and in the publishing and contributing to the research. With that, I would like to welcome Dr. Habibi. She's going to talk to us about the performance of multi-radar, multi-sensor system in monitoring precipitation and the extreme events. This is a new system that was developed by the National Weather Service because of its usefulness and because of the capability that it has. So Dr. Habibi is going to talk to us and share with us some of the conclusions and experience that we had in forecasting and monitoring some of the floods that the Houston area experienced. Dr. Habibi, the floor is yours.
Thank you. Let me share my screen if you stop yours. Okay. Okay, anyone? Is it sure?
Yep, we're good.
Okay, good morning, everyone, and thank you very much for participating in this research seminar, and thank you, Dr. Fares, for the introduction. And today, as Dr. Fares mentioned, I'm going to talk about our research, our recent research in natural resources and environmental science group. which is related to the performance of radar that developed by National Weather Service. And we are interested in seeing how this radar will or this product will perform under extreme events. So what motivated us to do this actually work was environmental extreme and climate variability, which basically result in increasing the chance of direct and indirect or indirect problems, specifically in a large and highly urbanized area like Houston. Which some of these problems are flooding, agricultural production, and these sort of things. All of these problems basically cause, significant economic problems, as well as, inconvenience and inconvenience and problems for the residents. One of these extremes is heavy precipitation, which causes flood. As we observed, as a result of climate change, these extremes or these heavy rainfall are increasing in both intensity and frequency. So it is necessary to develop an effective strategies for emergency flood management and response and flood management, like mitigation, response, and recovery preparedness. So to develop such a strategies in specifically for flood forecasting, we need both hydrologic models and availability of rainfall data, which basically without the rainfall data, we will not be able to actually do predictions, and which is required or is a baseline for making emergency decisions. So as all of you may know, we have rain gauges, which basically in every metropolitan area, those are available. But they do have some limitations for such a high resolution prediction, because we basically for most of the areas, we don't have a dense network of rain gauges. So that's why scientists and National Weather Service and other agencies try to develop products or gridded products like this product that I'm going to talk about. These are gridded rainfall data, which basically they are in high resolution, and they want to produce them in high resolution, both in spatially and temporal resolution. These try to answer or address these limitation with range gauge data. But before we can use these data for emergency management, we need to measure their accuracy in the modeling. So that's why we did this work. So basically, in this research, we try to evaluate or assess the performance of multi-radar, multi-sensor system compared to other products like rain gauges or MP product, which is another product of National Weather Service, at different temporal and spatial resolution. And we tried this and evaluate this for different events, major events that happen in Houston, in Harris County. And also we wanted to know the effect of these spatial and temporal resolutions on the performance of MRMS system with using some statistical indices. As I mentioned, we selected Harris County, and that's because of three reasons. One, it is the most populous county in Texas with a population of over 4 million people, and due to its humid subtropical climate, and also located near coast, we usually get a lot of rainfall and the extreme ones in this area. And the other reason is that there is lots of, or not lots of, brain gauge data installed in this area as we compare it to the other areas in the country. We have 42 rain gauges that is suitable for this comparison. The flooding events that we selected is for one, a Memorial Day event, which was 25 to 27 May 2015. Which in that day we had in some areas more than 500 millimeter rainfall, usually in southwest of Harris County. The other one was Tax Day event, is 17 to 18 April 2016, which in northern and western part of Harris County received lots of rainfall, and we had unfortunately 7 fertilities and thousands of damages in that day. And the well-known Hurricane Harvey flood, which caused a lot of damages, and we at some parts we received around 1,000 millimeter of rainfall. And the other one is Tropical Storm Imelda in 2019 September, which brought heavy rainfall, widespread flooding in southeast of Texas, and some areas more than 500 millimeter of rainfall. The data that we used are three different type of data. One basically is rain gauge that we use it because they are in a surface elevation. We use it as a truth data and the actual or the truth values. These data are in 5-minute temporal resolutions. We had 142 rain gauges available across Harris County. And the range gauges is basically using a simple method to measure rainfall. The left figure is a simple one that anybody can use to observe or measure rainfall. And the other one in the right figure, we see that these are the usual tipping bucket rain gauges that are installed in the area, and they are in 5-minute resolution. The other one is, as I mentioned, MRMS products. They are in 2 minutes and 1 kilometer temporal and spatial resolutions. They're coming from National Center for Environmental Prediction and in NOAA. And they started these products in 2014, if I'm correct. And since then it's in operation. And the other one is the MP data, which since 1996, the National Weather Service produced this product. They are in a lower resolution, 1 hour and 4 kilometer in temporal and spatial resolution. For example, for a multi-radar, multi-sensor resolution, how they actually produce is a combination of several things. One, radars that we have like 180 radars over United States. They use satellites and some of the rain gauges, lightning and model prediction, and climatology like wind and temperature and other climate data. They all combine, and this product is producing every 2 minutes. So the results that I'm going to talk about are categorized in 3 sections. One, we try to visualize this rainfall in these events, basically both time series over the county and maps. And then we categorize them in temporal aggregation effect and a spatial aggregation effect. In temporal aggregation, we had different scenarios, and for example, the county scale analysis combined all the events together and average it through the county. The station-based analysis, basically we analyze every station individually to see how they are working. And then the other is event-based analysis. We actually categorize every event separately and try to evaluate them. And MP and MRMS comparison to see how these products differ from each other, and the spatial aggregation effect. One thing that I need to mention, and I forgot to mention before, is that these products are different in temporal resolutions. As I mentioned, the rainfall data are in 5 minutes resolution, temporal resolution, or time step, and MRMS are in 2 minutes. So in order to compare these products together, we need to synchronize them. So basically, if I want to compare them in 5-minute temporal resolutions, I need to simply aggregate, MRMS data in 2 minutes to reach 5 minutes resolution. Or if I wanted to do an hourly comparison, so I basically need to aggregate both rain gauge data in 5 minutes and MRMS in 2 minutes spatial temporal resolution to reach to 1 hour temporal resolution. The first result is the time series of these products. What you are seeing here is basically four plots: one for Memorial Day, one for Tax Day, Hurricane Harvey, and Tropical Storm Imelda. The blue ones are MRMS product, red one is MP product, and the black dashed one is gauge observations. And we have the rain rate and the y-axis. So what we are seeing here is the first thing that comes to mind is that, okay, MRMS, it looks, for example, for Memorial Day and Tax Day event, the blue ones are more in correlation with gauge data. If you see the up and downs, it's basically follows the same. But we don't see that much in fall and downs in MP product. But what we do see in MP product is the rise in the peak flows. It kind of capture that peak flow better than MRMS ones. So one thing that we need to check on later for this, how this different. And for Hurricane Harvey and Tropical Storm Imelda, these are the more extreme events. So and what we see is basically both products, MRMS and MP, have a good prediction, have a good measurements on these both events. And then it's a good sign that these rise and falls and the peak flows are kind of matching with gauge data, but because it's a huge event, we need to look further to see what's going on with this products in each event or in each station. The other thing that we want to make sure is to have the maps, the special maps of all the products, basically in here, MRMS and gauge data. So MRMS is a gridded data, so we can plot that as a map. But for gauge data, because it's a point observations, we need to do some interpolation techniques in order to be able to interpolate for the non-gauge locations to basically map them and see how the patterns of these individual events. For this part, we did some analysis, use different techniques. The most famous techniques are inverse distance weighting, radial base function, ordinary kriging, and empirical Bayesian kriging. I'm not going to details of these techniques, but basically they try to use different functions to predict the non-gauge locations. What we used here in ArcGIS is the cross-validation function, which is basically it's from the all data points that we have. It basically removes one point and try to develop a model based on the remaining stations. And when the model is developed, it tries to re-estimate that removed data and do the statistical, indices, metrics like RMSE, R square, and those sort of things. And it repeated this thing for all the grid point, for all the observations that we have, and then try to average the statistical indices. And based on that, we can come up with the best technique here. What you see in the plot is the 4 techniques. The green one is radial base function. The orange one is inverse distance rating. And the blue and red one, which is kind of overlaid on each other, it's the ordinary kriging and Bayesian, empirical Bayesian kriging. Which both of them looks perfect among these methods. But if you see, for example, R square of ordinary kriging and Bayesian kriging is around it's 90%, and the RMSE is lower than these 2 other techniques. It's 14 millimeter, and a little this empirical Bayesian kriging is a little slightly better than ordinary kriging. So we selected that technique to introduce the interpolation among the gauge location. So what you see here is the left one is MRMS product, which basically we map it, and gauge observations that we use the technique, the selected technique to map it over the area. This is for Memorial Day event, and if you see it, it's basically the patterns look the same. We see in the south west the rainfall is higher, and gauge observation shows a little higher rainfall over this area, which MRMS didn't see that information or see that precipitation in this area, and it kind of underestimates rainfall in this area. And for the other one is tax day, and the same we see here in the west. We have a larger rainfall, but in MRMS we don't see that much of rainfall in this area, so it's basically again underestimated rainfall for this section. But the patterns basically looks fine together and matches. And the other one is MRMS and gauge for Hurricane Harvey, which here the pattern, it's not as much as good as the previous events. We see some patterns, but it's not that much of follows what we see in MRMS. And this is a heaviest rainfall, and we see for this extreme event, it seems MRMS are overestimating rain gauge data, overestimating rainfall, which we need to look further to see if that's the anticipation is, or what we actually see here is basically correct based on further analysis. And for tropical stormy Milda, it's basically both products have look, the pattern are the same, and we see the highest rainfall over the north east of the study area. Which is okay. So for this storm, we see that both products are almost on the same page.
So when you want two-way talking, then
okay. For further analysis for temporal aggregation, we first try to do the county scale analysis. What you see here is different temporal aggregations. 15 minutes on the left, 30 minutes middle, and 1 hour in the right. And basically all events combined in this analysis. So we didn't try to do the individualized the events. So we basically put all of the events together and plot it here. Which is gauge data in the x-axis, MRMS data on the y-axis.
In fact, I wanted to buy that VR camera.
So you see some indices or metrics for in each plot. Yes. Okay. So each plot, so we have R square, which is basically try to is the degree of collinearity between rain gauges and graded precipitation, and it also describes the portion of the variance in rain gauges data as explained by MRMS. It's sort of the agreement between the two products. We have correlation coefficient, which is how these data are correlated. It usually shows the up and downs in the time series. And we have error, which is basically how spread the data are. And we have a bias, which shows basically if it's positive, it's overestimate the data. If it's negative, it's underestimate the data, and we can get some those sort of information from these values. And we have FAR, which is a false alarm ratio, which is okay. For example, it says that if, for example, MRMS see precipitation in one area, but gauge data doesn't. So that's a false alarm. It says that okay, there is a rainfall in this area, but gauge didn't pick that information. That shows the false alarm ratio. And we have the probability of detection, which is basically both products have the same information. There is a rainfall in MRMS, and gauge data also cache that rainfall. What you see here when we compare these three scatter plot is that from 15 minutes to 1 hour temporal aggregation, R square gets better from 0.7 to 0.82. And also we see the same on correlation coefficient, 84 to 91 for correlation coefficient. But on the other hand, we see a significant increase in error, which is basically, I think it's based on that we have the error in a small scale, and when we aggregate it, we basically aggregate the error, and we increase the error, which basically we need to have a kind of balance between error and agreement and correlation between the products. Although we have a good agreement in higher in low temporal resolution, which is 1 hour, but we see high error in this aggregation. The other is a station-based analysis. We come to, take that, okay, what is each stations look like for these different, for each events. So basically it's the same. All the events are included in this analysis, but we basically did this for individual stations. So for example, the upper map shows the correlation coefficient for 5-minute temporal aggregation, and the lower one is correlation coefficients for 1 hour temporal aggregation. And what we see here is that, for example, for 5-minute temporal aggregation, we have a weak to a strong, correlation, 0.28 to 855. And we see, when we aggregate, we see 0.5 at the minimum and 97 at the maximum correlation between the, in the range, in the gauge locations. But what what a conclusion that we can get from this figure, this map, is that so there are a few locations like this one, and I map it here as well, that although we increase the temporal aggregation, which basically try to, it kind of improve most of the performance or the correlation between the gauge and MRMS, but there are some locations that didn't get better. which those locations might be, there might be a problem with the, range gauge observation, because usually these gauges are uses for operational measurement, and because they are, convenient and reliable tools. But they also have some problems. Maybe they have problems with tipping problems, or calibration problems, or maybe there is a tree kind of, grown that area that doesn't let the rainfall come to completely, measure the rainfall in that area. So those are stations that the ones that needs to be kind of observed or monitored, and see what is the problem for those stations that even though the aggregation didn't improve their correlations. And then also in the this histogram, which you see it on the left, you see different temporal aggregation, which is the 5 minutes, you see it in the map, and 1 hour, you see it on the lower map, and the other 2, 15 and 30 minutes in orange and green, you see that how the correlations are improved over the aggregation effect. And although, you see we have increasing the aggregation, there are a few stations that still doesn't perform well. And in the next part, we came to analysis to do the event-based analysis. So basically try to separate all events and see how they perform individually. For all of these figures, you see a correlation coefficient in upper left, R square on upper right, RMSE lower left, and percent bias in lower right. So Memorial Day, in all this graph, Memorial Day event is in blue, tax day in orange, Hurricane Harvey in green, and in red is Tropical Storm Milda. So if we see on the correlation coefficient along with R square, we see that among all of them, Memorial Day in blue has the highest correlation coefficient. That's one of the things that we also observe into the time series, that the up and downs, it's the best, and also the time that come to get the peak values. The agreement of the with gauge data, it performs the best more than the other events, followed by tropical storm Imelda, which is in red, which when we actually aggregate from 5 minutes to 15 minutes, 30 minutes, and 1 hour, which we see it in in x-axis, we see a partially improvement for all the event, but mostly for Memorial Day events. And we do see it in R square and correlation coefficient. But when we see in the error, it's the Memorial Day event. It's not as much good as tropical storm Imelda. So it has the tropical storm has the lowest error for all temporal aggregations: 5 minutes, 15 minutes, 30 minutes, and 1 hour. And among them, tax day and Hurricane Harvey, we see the largest error during the aggregation, and it's getting worse and worse when we aggregate them. And about this percent bias, one thing we can get out of it is for Memorial Day event and tax day, which both of them are the lowest intensity compared to tropical storm Imelda and Hurricane Harvey, both have a negative large percent bias, which basically shows that they underestimate rainfall for those events. But for Hurricane Harvey and tropical storm Imelda, which are the more extreme event than the previous ones, are actually overestimate rainfall. So one thing that we can conclude from this slide is that Probably MRMS data or MRMS product will overestimate significant or extreme events and underestimate lower intensity rainfall like Memorial Day and Tax Day events, which basically it's kind of useful for forecasting if there is a huge event or there is a low intensity event. It's kind of helpful to know how these product will actually perform. We did some limited analysis between MP and MRMS. As I mentioned, MP is also a National Weather Service product. It's started in 1996 and it's a 1 hourly and 4 kilometer special resolution compared to MRMS. It's a lower resolution product. So we tried to compare these two products because MP is a 1 hour product. We need to aggregate MRMS to a 1 hour aggregation to be able to compare these two together. So what you see in here is gauge observation in x-axis and MP and MRMS product in y-axis. The red ones, the red dots are MP and the blue ones are MRMS data. And we see the indices as well in the color red and blue, which belongs to MRMS and MPE for each indices. The top ones, Memorial Day and Tax Day event, when we compare it with Hurricane Harvey and Tropical Storm Imelda, it shows that at 1 hour temporal aggregation or resolution, both products, MP and MRMS, are showing a better performance with these two events, as it is actually shown in R-square, both almost 82% for Hurricane Harvey, and here it's a little MRMS products is a little bit lower. It's 77% compared to 81% of MRMS data. And on the other hand, if we compare correlation coefficients, both are 92% and around 90% in Hurricane Harvey. So it performed well for Hurricane Harvey and Tropical Storm Imelda. Both of the products are for this event are somehow performed the same. But for Memorial Day and Tax Day event at 1 hour resolution, it's a little bit different. We see that a correlation coefficient is they are correlated for both events, but R-square RMS data it's a little bit lower, and also for Tax Day event, you see that it's not a good performance, 56% and 43% agreement for this product. And also if we kind of see the error, both products have almost the same, somehow the same error when we compare it with the Hurricane Harvey and Tropical Storm Imelda. Also the error is kind of the same for all of them. But if we did some analysis to see in overall which one of these might be better in 1 hour temporal resolution, if, for example, one of them is not available or anything, if there is a way we can use the other one. So we can actually conclude that MP and MRMS both can, quantify rainfall accurately for low resolutions at 1 hour resolution. And also, but a little MRMS seems to be overall a better product compared to MP data. But again, for flood forecasting, which is time matters, this product at this low resolution, low temporal resolution, might not be useful. But for some basic analysis, like reservoir rules or some simulations for different management, not flood forecasting, some other management strategies, might be useful, but for flood forecasting, it's better to use a higher resolution product. In the next step, what we did was a special aggregation effect. So what does it mean is that we basically try to aggregate rainfall, aggregate data over a special resolution, different special, 5 kilometer, 10 kilometer, 15 and 30 kilometer. Which is basically combined or aggregated all data points that are fallen or exist within each grid cell. So, and obviously when we have a high spatial resolution, for example, 5 kilometer, we might have just one gauge observation in each. But if you compare it with 30 kilometer, in each grid box, we have more than 20 or 15 gauges that we can, aggregate to reach to the special aggregation effect. So the higher resolution, the lower resolution special special resolution, higher the number of gauges that we need to aggregate. So here is the result of a combination of a spatial and temporal aggregation. So what you see is basically for all of these 6 plots, spatial resolution are in a y-axis and temporal aggregation are in x-axis, 5 minutes to 1 hour. And here we see 1 kilometer, 5, 10, 15, 20, and 30 kilometer. And we keep the scale the same for all the indices. And this is R square correlation coefficient, probability of detection, and some correlation, some other statistic for index for probability of detection. And also there is an error here and false alarm ratio. If we look in detail in these maps, these heat maps, is that, for example, in 5 minute temporal aggregation and 1 kilometer spatial aggregation, which is this blue one, R square is 55%, and correlation is 75, almost 75%. And when we increase the spatial aggregation, we have a better performance in both R square and correlation coefficient. If you see 55% reach to 81% in R square, 74% to 90% in R square. And when we try to have a combination of these two spatial and temporal aggregation, the better performance are here. Almost 90% at 1 hour aggregation and 30 kilometer aggregation, spatial aggregation. And we have the same pattern in correlation coefficient. And also almost for the other POD and CSI are the same patterns. But when we compare this map with error, we come to a good conclusion. For example, if we see R square, for 5 minute temporal aggregation and 1 kilometer, we have a 71 millimeter error. And when we aggregate especially, the error decreases. And that's a good result here, which shows that although we aggregate over spatially, we don't see error actually increases. And also if you see it gradually for temporal aggregation 5 to 1 hour, in 1 kilometer error is gonna increase here. And the largest error is in 1 hour temporal aggregation. So one thing that we can get out of these maps altogether is that the spatial aggregation are more effective in higher temporal resolutions, 5 min, 10 min, 15 min. And when we increase it, although the agreements is getting better, but we at the same time we increase the error and the spread of the variance of the data points. So if we are going to do a special resolution or special aggregation, it's better to use it for higher temporal aggregations up to 15, but larger than that, it's kind of a mess up with error here. In conclusion, what we see here is that MRMS product tend to underestimate higher precipitation rate and overestimate low intensity precipitation. And temporal aggregation at a higher resolution, it's kind of resolve some underestimation, but at the same time, it increase error. And MRMS and MP both accurately can estimate precipitation, but MRMS is a little bit better for at 1 hour temporal resolution. And special aggregation are more effective at high temporal resolution than the lower ones. And this work actually submitted to a journal for publication, which is still in under reviews. But we use the result of this work for our future work, which is basically try to use MRMS and other precipitation events to actually identify the watershed response to heavy to extreme rainfall event in Houston area. Which we try to use a warp hydro, as Dr. Fares mentioned before, for simulating and using the MRMS product and other available products to see how the stream flow look like at the end of the downstream of this catchment. And we do have two Great Lakes here, which basically we try to actually do some analysis to find out the best reservoir management rules in this area and see what is the best rules that we can come up in order to have more accurately a flood prediction at the outlet of the catchment. In addition to that, we can have some other analysis like, try to find out the impact of climate change and urbanization, land use changes on hydraulic and hydrologic response of the urban catchment. What we are going to use is warp hydro, which is a better and advanced model developed by National Weather Service, which basically in past they used HLRDHM, which actually was my PhD work. I used HLRDHM for prediction of flood, but HLRDHM has some problems. It cannot have a higher resolution as warp hydro can. The highest resolution in RDHM was 250 meter, but in warp hydro it can be reached to 100 meter. And also there are a lot of availability in warp hydro, which is the type of routing, which can be both reach-based routing, grid-based routing for this analysis. So basically, warp hydro have both rainfall runoff modeling and routing for the simulation purposes. So what I have here, I found this in UCAR website. This is a Colorado flood at 15 September 2013, and it's a good representation of warp hydro. What you see here, the shades one are the accumulated precipitation, and the green, the stream ones are also, it's obvious here. So that and what you see here is a good representation of what a warp hydro is capable of, and how dense and how detailed it can predict floods at the downstream location, and also in any areas of interest that we are looking for prediction and management flood prediction. So that's what we are actually goaling, or we are accounting for, and we are doing to get the best out of this model and try to have it set up for Houston area and do some interesting and exciting simulations and results out of this work. And the work that I kind of presented is supported by Texas A&M AgriLife Research and Evan Allen project. And that's it. Thank you very much for listening, and I can take any questions if you have any.
Well, thank you, Dr. Habibi, for a nice and detailed presentation. So the floor is open for any question for Dr. Habibi. Please feel free.
Dr. Ferris, may I ask a question?
Yes, please go ahead.
I don't understand all the details, but would wind speed be a factor in affecting the accuracy of predictions? Because if I understand correctly, each raindrop gets into the gauge, but if there is a wind, wouldn't it affect the accuracy? For example, if you increase the temporal and spatial resolution, obviously the averaging will take care of the error. So probably your model behaves better under those conditions. Habibi pointed out one factor, trees. So I was wondering about wind speed too.
Yes, what I think is that yes, wind speed, that's a good question. Wind speed is definitely kind of affect the truth data, or also the gauge observations, the gauge observations for for rain measurement. So, but because most of these gauges are they are basically placed in an open space place, but which might not that much of a wind speed coming on the ground, because usually wind speed are in 2 meter level of kind of measure at a 2 meter elevation, and it might be get higher at that level, but on the ground it's might not that much of effective. But I agree with your point. It's kind of change a little bit the truth values. But for grid data for radars, because some of these, for example, MRMS will account for wind speed, temperature, and other climatology data. It's kind of see that effect on rainfall prediction. So yes, my question is that it's definitely affects. It might not be that much of truth data, but at least we have some idea how much of rain we receive on the ground, which we don't have any other choices that I agree and have it as a truth data. And I don't know if Dr. Faris can add anything on this.
I think your answer is correct. However, there is, and I was looking right now on my one of my lectures, I show standard rain gauges that National Weather Service uses, and around the gauge there are some protection to minimize the impact of wind on the catchment of the rain gauge. So wind speed is important, especially in evapotranspiration and calculation. But yes, Dr. Habibi, that's correct. That's the one on the right-hand side here that you see. Those are to protect the rain gauge from the effect of winds on the catchment of the rain gauge.
Okay.
Yes.
Thank you.
You're welcome. I think another additional comment is we shared this results with the National Weather Service and with the Severe Storm Laboratory of NOAA. So they are responsible for developing the MRMS. We shared the paper and we had a good discussion with them, and they gave us some feedback. And the reason for sharing was to not only share the work, but at the same time, getting them to know that we are actively working on this area. So if there is a funding or an opportunity for us, then they should consider us or collaborate with us. So I think this is a suggestion that I suggest for my colleague. If you have something relevant to some of the federal or state agency, it's very important to share your work with them so that they know that you are doing something in that area.
This is Dr. Nag Chaudhary from University of Maryland Eastern Shore.
Hey, good morning, good afternoon.
Good afternoon, good afternoon. I have to touch base with you also, like I've been sort of tied up for the last few days quite a bit. But I had a quick question for Dr. Habibi. If
sure. I thought you were gonna give us a preview of next week.
I'm going to put together something very soon. But mine will be more of what technologies we have used in our setup for precision agriculture.
I'm glad you are able to join. Please go ahead and ask the question.
The question is who is responsible for the calibration of these gauges? And also whether you are deploying the gauges yourself or somebody else is actually putting the gauges in the field. The other question is I'll just combine both of them so that you have, I don't know whether I'm phrasing this right, but I'm wondering when you're doing the spatial interpolation, let's say with IDW or creeding or whatever technique you might be using. So is there some gauges that you separate out as the validation set, and so that you can verify whether the the interpolation that you did actually worked out, and those you did not really use in the interpolation before. So you sort of separate out into a validation set and a calibration set. So
okay. So in response to your first question, all the gauges are installed mostly by Harris County Flood Control District. They have a flood warning system project, and they actually try to install all of these gauges and calibrate them. So it's their responsibility. We took the data. But also we, as a project, we try to install some of these, a few, I'm not sure how many right now, but I participated in one to install these gauges and see how the process is. But basically, most of them are based on the responsibility is by Harris County Flood Control District. They have a website and a kind of live map for each of these stations, and you can gather the data, extract the data, and use them. So basically, I just use the data and got the data from them and use them. But basically, they do the calibration themselves and then make sure that the results that are public are in a good, way. So that's for the first question. For the second question, if I may, so I use different techniques and I use it in GIS. GIS has a good method or good toolkit for cross validation function. So what basically it uses, for example, I have hundreds of data, let's say hundreds of data points that I need to develop a method and see what kind of techniques, interpolation techniques, might get a better result. I can get a better, interpolation values. So what it uses is a cross validation function. So basically, at one step, it's remove one station. For example, I have 100. It remove one, and it's develop the model based on 99 stations, and try to develop a model and predict that one value, one station that is out of the calculations, and try to analyze or have the statistical indices, calculate that is statistical indices, right? RMS, R square, or other indices that I haven't bring it here. And then it reiterates this for all of the gauges, all of the 100 points that I introduced to the model. So basically, it do this for 100 times, remove one, and calibrate the model and estimate or validate it by that data point. And when it does this, at the end, it's coming up with an average statistical analysis and say that, okay, so what you see here is based on the average of this cross-validation.
Okay,
thank you for the questions, and thank you for the answers. And we are looking forward for next week. So you've heard our speaker. So for the rest, who's going to be talking to us next week at this time, 11 Central Time, about some aspects of precision agriculture. I think we are 5 minutes past 12. So time for lunch. We really appreciate everybody's contribution, and we thank our speaker, Dr. Habibi, for an in-depth and fruitful discussion that we had and good presentation. So with that, please join us next week and continue joining us and supporting the research seminar series. Have a great afternoon. Thank you.
Bye.
Dr. Faris, I have a quick request from you to you. I don't use Zoom too much. So is there a way that the two of us could get together sometime and make sure everything works out well?
Will do.
What would be a good time?
Let's talk right now. Let's after everybody goes, we'll talk.
Okay.
Can you hang on for a minute, please?